All right, can you all hear me okay? Yeah. Okay. Okay, so I'll use it. Don't press only the bottom button, right? Okay, great. So, well, apologies to the other speakers and Shayna and Hetty, for hearing everybody's jokes, 3 days in a row right now. But in any case, I just wanted to first just say thank you. These days, so much really the speaking engagements I do are related to PFAS. So it's really nice to have an opportunity to go back, not to the basics, because none of this is basic per se, but to the more traditional contaminants and speak about bioremediation here. So Paul gave us a really great introduction to, remediation strategies in general, and certainly regarding monitored natural attenuation. But bioremediation and biodegradation is such a huge part of natural attenuation that in speaking to broadly here about bioremediation, it's hard to not really talk about natural attenuation a little bit more. And really just want to highlight here, there's a whole bunch of different natural attenuation processes, but we can kind of group them into two broad categories. So on the left here, we've got non-destructive natural attenuation processes, and then on the right there, we have the destructive natural attenuation processes. And all of particularly the non-destructive processes, these are really happening at virtually every site to a certain extent, at least, right? Absorption to the aquifer media, dilution, as we have clean groundwater sort of moving through into our plume. So all of these things are really at play and can really change the dynamics depending on, which are stronger or weaker. And all of this really plays a huge role in what you see over time for these contaminated sites. So of course, here I'm going to be focusing on biodegradation for the remainder of the presentation here. And, I promise we didn't coordinate this, but, you'll see there's a lot of repetition amongst some of our presentations here today. And it's just really because these are some of the most critical pieces of the puzzle here, right? So, over time, we can demonstrate what sort of natural attenuation processes are happening. This can be as simple as just looking at historical data trends, right? Are your contaminant concentrations decreasing? Are you seeing that increase in daughter products and decrease in parent products? Are you seeing depletion of electron donors or receptors? Things of that nature can really help you sort of make the case that either biodegradation or natural attenuation from other means is happening here. And then, of course, you can also look for the microbial data to show, we have the bacteria present at sufficient quantities to have that natural biodegradation occurring. And as Paul was sort of talking about really at the end there, answering the questions on, rubrics and things, there's a lot of sort of non-technical factors that make in situ approaches and in situ bioremediation specifically really attractive for a lot of sites. When we're comparing in situ methods versus ex situ methods, there's usually a really dramatic decrease in the carbon footprint associated with that in terms of just energy usage. There's also usually much less infrastructure required. And for that, I'm not really talking about like a dig and haul where you have an excavator there for, maybe a couple of days or weeks or something, but really more comparing that to, say, like a pump and treat system where in all likelihood you have the infrastructure for that out on your site and it's there for likely decades, right? On top of all that, I will say that I had a sort of brief stint in environmental insurance doing pollution liability insurance. And a huge concern amongst that community, which is really sort of a canary in the coal mine sort of what we should all be concerned with these sort of exposures, is the handling and transportation of any hazardous waste, as well as the final disposal locations. And the liability associated with that, we all know how circular liability works from cradle to grave, and that doesn't go away just because you now have it off your site. So just other things to consider. Then on top of that, generally speaking, again, these in situ methods, even if you maybe in some scenarios have to do multiple rounds of application, generally speaking, the actual operation and maintenance that's required is pretty minimal. Really, it's just going to be monitoring, what kind of concentrations you're seeing over time and maybe geochemical shifts and things of that nature. But in all likelihood, not having to do, big cleanouts and carbon exchanges and things of that nature. So what exactly is bioremediation? Essentially just using microorganisms, bacteria and fungi technically, though bacteria are really the most favorable for the contaminants we sort of see in day out, to destroy and detoxify contaminants. And we can do this in a bunch of different ways, both in situ and ex situ. We could do some sort of land farming application or biopiles, or what I'm going to be focusing on here today. My area of expertise here is on in situ bioremediation. And a little bit on just the nomenclature here. So biostimulation is really where we're just encouraging whatever indigenous bacteria are already present to metabolize our target contaminants of concern, right? So this might be by adding nutrients or adding electron donors or electron acceptors into the mix to encourage the bacteria that are already present to really do their thing. Versus bioaugmentation is where we're specifically adding in bacteria into the system, either because they're not present or because they're not present in sufficient quantities. And often we're doing these things sort of in concert to really make sure we have the system sort of fully covered. And really what we're relying on here is these couple oxidation and reduction reactions that these bacteria perform to live, and ultimately they exploit these reactions to thrive, and that ultimately results in reductions of our contaminants of concern. So a little bit of a chemistry lesson, hopefully no high school flashbacks and nightmares here, but essentially just want to lay out here what I really mean by these oxidation reduction reactions, right? So we have on the left here, an electron donor that is going through an oxidation process, giving that electron to an electron acceptor, and then sort of conversely, the reduction mechanism, where we have a reduced electron acceptor. Hopefully that all makes sense. So there's a wide range of contaminants that are applicable for this type of remediation strategy. This is a list here. I know it's probably kind of impossible to read, but I'll give you a summary overview here. I've kind of lumped these into sort of three categories. So on the top left, these are your petroleum hydrocarbons. Then below that, some of the fuel additives, and then on the right here, chlorinated solvents. And what you'll notice is that petroleum hydrocarbons, by and large, can be biodegraded via both aerobic and anaerobic mechanisms. Sort of same thing goes for most of the fuel additives versus the chlorinated VOCs. It's really, by and large, the anaerobic biodegradation mechanisms that are at play here. And really, this sort of boils down to, the petroleum hydrocarbons are compounds that have existed in nature for some, millions of years, right? So there's lots of different bacterial populations that have evolved to really use it as a fuel source, versus the chlorinated solvents have really only existed for maybe a little over 100 years now, right? So there's way fewer bacterial populations that have evolved to really use these in an energetically favorable way. This is a little hard to read, but really just wanted to direct you to this resource from the EPA, which is essentially just a guide and an introduction to in situ bioremediation of groundwater, and just sort of goes through some of the various bioremediation mechanisms and some of the key advantages, disadvantages, and just kind of considerations to take into account. I just encourage you to visit this resource if you haven't explored. All right, so starting with aerobic bioremediation. So typically here we're speaking about aerobic bioremediation of petroleum hydrocarbons. And as the name sort of suggests, this is happening in the presence of oxygen, where we have, again, mostly petroleum hydrocarbons. The sort of low to moderate weight petroleum hydrocarbons are usually the most readily biodegradable via this mechanism. And the end products here of this aerobic respiration process are carbon dioxide and water. And usually we are most limited with this process by the actual electron acceptors, in this case, oxygen, that are in the system. There are other nutrients and things that are also needed, but that is very rarely the sort of limiting aspect here. And just have this chemical equation here for the for benzene, how this would be aerobically degraded here. And you can see this sort of explaining why those electron acceptors, in this case oxygen, really is that limiting factor here. For every single mole of benzene, we need 7.5 moles of oxygen to mineralize this here. Now, that was, sort of the most energetically favorable bioremediation process for petroleum hydrocarbons. But there's lots of other mechanisms that play here. Particularly, we're still in this oxidative state here, but oftentimes oxygen is depleted very quickly in these petroleum hydrocarbon plumes, again, because it is the most energetically favorable degradation strategy. So what happens naturally is the oxygen is all consumed really in your source area, and then other electron acceptors that are happening in the absence of oxygen are then consumed. So this is still an oxidative process, but it's anaerobic without oxygen in the system. And this is happening usually intrinsically at most petroleum hydrocarbon sites, where again, oxygen has already been depleted. So the bacteria will sort of go down a ladder, so to speak, from the most energetically favorable electron acceptors to the less energetically favorable electron acceptors. So this image here is just kind of showing a snapshot in time, sort of spatially out from your source area down toward your more sort of dilute end of the plume. But you could almost think of this too as sort of over time if you were just looking at the source area. And essentially, we have our most energetically favorable process where the bacteria are using oxygen, then they're going down to nitrate, then iron, sulfate, and ultimately we get the methanogens that are active sort of as the least energetically favorable reaction here. And again, we can kind of group these different electron acceptors and the bacteria that use them into two different categories, where we have our aerobes, obviously things that are happening in the presence of oxygen, and anaerobes that are active in the absence of oxygen here. And really just want to point out here that there's no one organism, bacteria, that is going to be able to reduce all of these electron acceptors, right? A lot of them are present naturally, and on both petroleum hydrocarbon sites, this is not the limiting factor, right? The presence of these bacteria, they are very ubiquitous. But really what is helpful to note here is that we can monitor all of these terminal electron acceptors to sort of use diagnostically, like where are we at in the natural attenuation process of this plume? What processes can we potentially encourage here to achieve a more robust biodegradation strategy? Now, switching gears here a little bit into anaerobic bioremediation in a productive capacity. So before everything, even when we were talking anaerobically, was still these oxidative reactions. And now sort of switching gears here. And typically we're using these processes for things like fluorinated VOCs, where biologically available organic carbon, which, there's some amount of it that's naturally present, but often we're adding that in when we're doing these bioremediation strategies, is added to stimulate all of this activity. That organic carbon source, or the electron donor here, creates and sustains these anaerobic conditions that are needed for these bacteria to perform these processes. They consume the oxygen and the other electron acceptors during its biodegradation itself. So ultimately, what we're doing here is encouraging that bioreduction of our chlorinated, these oxidized contaminants by generating hydrogen through the fermentation of these organic carbon sources. And really, generally speaking, so part of why these chlorinated VOCs are not really susceptible to that oxidative processes that, they themselves are already sort of in an oxidative state. But in any case, the chlorinated solvent in this scenario is acting itself as the electron acceptor. So before we were adding in maybe or using the naturally occurring electron acceptors for the degradation of petroleum hydrocarbons. Here we're sort of flipping the script a little bit, right? And the chlorinated solvent itself is acting as our electron acceptor. And there's various bacteria that can use these oxidated contaminants in these respiratory mechanisms and gain energy from that. And that's why they're able to proceed. Now, really was talking almost exclusively about organic contaminants prior to this, but just wanted to point out that the most commonly anaerobically reduced inorganic contaminant that we sort of see as practitioners, hexavalent chromium, where this is a relatively easy process to induce, where we add in an electron donor and can essentially reduce the hexachrome to trichrome, so making it less soluble and therefore less concerning. All right, so bear with me on a kind of goofy little animation here, sort of running through what that reductive dechlorination process looks for these fluorinated solvents. So in this case, this animation is, you add in some fermentable source of organic carbon here that goes into solution. Then this fermentation reaction happens, right, where we're able to generate the hydrogen that the microbes actually need for the biodegradation of our fluorinated solvents. So once we have the hydrogen now readily available in the system here, then say we have a PCB molecule here, it will, sort of come in contact with the appropriate bacteria. And once hydrogen is also there, that anaerobic bioremediation process is sort of sequentially plucking off each of the chlorine atoms, and we end up with our non-toxic end product of ethene at the end there. So one more. And yeah, there we go. So broadly speaking, the most ideal site for bioremediation strategies are sites where, to a certain extent, some natural intrinsic bioremediation is already occurring, because then we know the conditions are generally favorable for us to sort of just, increase the throttle a little bit and maybe encourage things to go a little bit more quickly, a little bit more efficiently. But that's not necessarily the end all be all. There's certainly plenty of sites where biodegradation is not really happening readily that we can absolutely be successful with a bioremediation strategy. Another component to this is just having an accessible unit, whether that be because of, infrastructure that's hopefully not in the way, or just an appropriate depth that we can readily get to. Typically, the type of sites that I'm getting involved in, we're most commonly doing these applications with direct push technology, though we can certainly do things via wells and other sort of delivery mechanisms. But in any case, things often are sort of most efficient from a cost and time perspective. If we can relatively get to the contaminated zone with a direct push rig. The other thing to consider is just having, the appropriate geochemistry, and again, sort of similar to my top point on biodegradation already occurring, having the appropriate pH levels and sort of being at the correct rung on that sort of redox ladder is really helpful. These are challenges that we can overcome if needed, right? But it is something that we need to know sort of on the front end, and certainly adds to the complexity of the overall scope. And then of course, just the size considerations, right? And this is for really any in situ strategy, not just for bioremediation. But the overall size of your team is going to have a direct influence on, what kind of geometry makes the most sense and whether this is ultimately a cost-effective strategy. And then on the right here, really just sort of pointing out here, there's a wide range of different ORP ranges where that reductive dechlorination process can happen. So that's what, this arrow here showing. It's a pretty wide range, basically, as long as you are in mildly anaerobic conditions, this process can happen, but there is a much smaller range where it's optimal, right? So we're trying to make sure we can kind of engineer the system to maintain those optimal levels. So I wanted to, this graph is, I'll explain sort of what you're looking at here in a second, but really wanted to give you all a snapshot of sort of how to manage expectations for doing these types of reductive dechlorination projects. This was a study that we did at REGENESIS a few years ago, specifically with our 3D microemulsion electron donor, but the same logic would apply with different electron donors here. Really just want to point out kind of over time what you can expect to see and sort of, again, managing expectations. So what you're looking at here is the gray bars are showing our actual contaminant level and the amount of time it took to reduce the concentrations by 90%. Okay, so for example, it took 108 days for the PC concentrations that, this is average across 100 sites, but it took 108 days on average for PC concentrations to reduce by 90%. 148 days for TC, 213 for cis, and 304 for vinyl chloride. Now, the other thing that this graph is showing here is the amount of time it took to reach the peak concentration of these various constituents, right? So for the PC and TC, the peak concentration was at baseline, right, before we even did our application here, versus the cis and vinyl. The cis, we saw our peak on average at about 62 days, and then for the vinyl at 119 days. So, and this all, sort of follows the logic of what we're trying to encourage to happen here. We're sequentially going from our parent compounds to our daughter products, and along the way, we have those daughter products appearing as intermediates. And this is both encouraging, but also, if not interpreted correctly, can seem concerning, right? If you're given a data set at the 3-month mark, and it's like, great, we are seeing some really good reductions in parent compounds, but what's going on? We have all this vinyl and cis now. Sometimes it really does just take giving it a little bit more time to really work through the process and get to that complete degradation. Now, on the flip side, if you're looking at data from 2 years later and you're still seeing, super elevated concentrations in cis and vinyl, maybe you do need to go out and potentially do another application or sort of do some more diligent monitoring and see, do we have much of our electron donor left, and maybe sort of see where you're at, right? All right, so I wanted to just kind of touch on some of the data that is needed or desired at least before implementing a bioremediation strategy. And a lot of this gets to what Paul was talking about before. The conceptual site model is key and really is the end all be all for all of this. Everything else is kind of nice to have. But once we really have our heads around the situation, a really good conceptual site model, then everything often really falls into place very nicely. So understanding that, again, every single site has a lot of geologic heterogeneity, even for sites that we think are more homogeneous, there are always zones that have higher and lower permeabilities. So having a really good sort of high resolution data set can be extremely helpful. Understanding that the primary, secondary, and effective porosities is huge. And then really did want to highlight sort of this last thing here on the anthropogenic conditions. So often we are implementing these in situ strategies because, doing a major excavation or whatever is not feasible because, we've got lots of neighbors around the property, or it's a pretty just densely developed area already. And what comes with that? Well, that comes with potentially, like underground utility lines and potentially reworked soils and historic fill that's been deposited in places that doesn't make any, natural lithological sense, right? And all of this really needs to be well accounted for. And it really helps us actually achieve success when we go into the field to actually apply these remedies. Another sort of key thing to consider, and Paul's going to touch on this later too when discussing permeable reactive barriers, but so often we're doing, even for bioremediation strategies, we're doing things in sort of a barrier configuration. So wanted to touch on it here as well. That when we're implementing these solutions in a barrier configuration, mass flux is hugely important, right? Not just understanding sort of geospatially where your contaminants are, but the rate at which they're going through a specific area is hugely critical. And it's just a kind of general rule of thumb, about 80 or so % of your contaminant mass flux is often going through a 20% zone of the aquifer, right? So understanding that can really help you dial in your remedial scope, potentially dial back the cost, but also just enable you to hopefully achieve success. One of the ways that we really like to see this data collected are with passive flux measurement tools. We at REGENESIS have one called Flux Tracer. There's also passive flux meters that do, effectively the same sort of thing here, where essentially you put this device into an existing monitoring well, you let it sit there for some period of time, yank it out, usually a couple of weeks later, send it off to the lab, and we can get sort of discrete data at different vertical zones across that well screen of both the Darcy velocity and the contaminant mass flux directly. So these can be extremely helpful tools that are relatively inexpensive and easy to use for further data collection. Of course, and again, Paul already touched on this and we're all going to talk about it, but having really good, just like your field founder, PHORP, conductivity is so important for understanding sort of where we're at and what the existing conditions are. Getting your other terminal electron acceptors, right? The oxygen, iron, manganese, nitrate, all of that is hugely important as well as it's, I'd say, nice to have on the front end, but not as critical would be some of the other sort of end products like methane, ethane, carbon dioxide, so that you can kind of track those concentrations over time as well. Certainly, if we're doing a strategy wherein we're adding in an organic carbon source, so when we're doing enhanced reductive dechlorination, getting baseline on the total organic carbon is also really helpful so that we can track that over time. Your VOD, fluoride, and of course the microbial analysis is also really nice to have on the front end to sort of see, are the microbial populations already there in sufficient quantities that you maybe don't need to bio-augment. With that said, bio-augmenting is often a relatively inexpensive sort of insurance policy for these kind of strategies. All right, and then sort of on the back end, right, what do you need in terms of performance monitoring? I'd say really more than anything, not even any of the specific parameters, it's just having a good performance monitoring program established on the front end and understanding what questions you're trying to answer with that performance monitoring. That's really going to be critical for understanding, whether things need to be tweaked and whether you've ultimately achieved the site goals. For aerobic bioremediation, it's sort of like it's a lot of the same things, right? You want to understand the oxygen concentrations, the various other terminal electron acceptors, and of course your contaminant levels. For anaerobic, a lot of the same things, but also organic carbon, the contaminants of concern, of course, and the bacterial populations ideally as well. And typically, in terms of monitoring frequency for these sort of things on the front end, we like to see some pretty frequent monitoring so that we can see these changes over, maybe quarterly for the first bit, but then after that, certainly I still rarely get to dictate what the monitoring program actually looks like in terms of temporal frequency. But, a lot of data on the front end is really helpful and then can sort of taper off over time once we've established what kind of trends we're seeing. All right, so some logistics and other things to consider with these type of remedies. Bench and treatability and pilot tests are all great and can really help inform some of the decision making. But I'd say my piece of advice in general with all of these is to go into a bench test with a specific question in mind, not just doing a sort of science experiment and seeing what happens. That going in with a sort of hypothesis that you're questioning or something that you're specifically looking to learn really helps make sure that you're not just doing a bench test for the sake of doing a bench test, but actually trying to really gather specific information. For a pilot test, I mean, I love when we can do pilot testing. Obviously, it's not always feasible for every site, but it really helps inform, you know, what kind of radius of influence can we expect and what sort of flow rates can we anticipate. And it really just helps us then when we ultimately go out to do a full scale application, everybody is so much more informed and well equipped to do it in an efficient way without on the front end having to have a few days where we're just kind of figuring things out. So a little bit here too on just sort of some geometry considerations. This is kind of applicable to any in-situ strategy, and bioremediation actually is a little bit more forgiving on this than some other strategies. But in general, we're often doing a quote unquote sort of grid layout for source areas and things versus a barrier usually at sort of a distal end of the plume. And there's some trade-offs there in terms of the cost effectiveness of things, but really just kind of wanted to point out more than anything here that getting good overlapping coverage is key. It's, again, bioremediation can be a little bit more forgiving on this. It's not as dictated by having perfect contact because a lot of these reagents can move around a bit too. But in any case, just something to consider when it comes to overall application volumes and point spacing. And then just lastly here on circulation systems, this can sometimes be a really effective way to implement these types of remedies when you have either sort of space conditions or hydraulic conditions that make doing sort of a more standard injection approach less effective. And just kind of wanted to run through a couple scenarios here, sort of moving along the plume, right? So if we're in the source area, some of the challenges we're dealing with, maybe you've got some DNAPL and lots of stored mass, high concentrations, certainly, right? We potentially have a lot of diffuse mass into some of those lower permeability zones as well. And of course, you know, in our source area here, we're concerned about the overall plume generation. So what we often see is this is where we would, you know, potentially implement this in kind of a grid configuration. Versus as we go a little bit farther down gradient across our plume, maybe we're at the site boundary and our concern is more like the offsite liability of this thing continuing to migrate. Then we're dealing really more often with some of these high levels of dissolved concentrations, but less of that, less likely to have NAPL or super high concentrations. And we're dealing still with this diffuse mass into those lower permeability zones and the movement through the high mass flux zones. So what we can do here is, you know, either a barrier or a series of barriers to help mitigate that. And then lastly, you know, it's sort of similar, but if say we have even farther down gradient, but like a specific sensitive receptor that we're trying to protect, this is also another scenario where a barrier configuration can make a lot of sense. The challenge here usually is that we're targeting usually really low concentrations, right? In your source area, maybe the goal post that we're setting is, you know, a couple orders of magnitude reduction in the concentrations is usually a big success in a source area versus at the down gradient end here before, you know, a drinking water well or something, we're trying to get to MCLs. All right, switching sort of over to kind of some of the real nuts and bolts of the applications and things to consider for any direct push technology scope of work. The appropriate choice of injection tooling is something to really consider, and not necessarily even give it too much thought on the front end, but to be well equipped in the field with lots of different options that your team can be flexible during the application when inevitably you uncover conditions that you maybe weren't expecting. In addition to that, making sure that during the injection itself, some really high level monitoring is occurring, you know, on a really basic level, making sure that any of the wells in the surrounding area are just maintaining their integrity and you're not getting leaks from around them and things like that. But also looking at the flow rates and pressures that you're seeing at various injection points and any sudden changes in particular in those flow rates or injection pressures can really be telling in terms of what's actually happening in the subsurface. And then from a groundwater quality perspective, changes in, the ORP and the DO, the pH, sometimes depending on what sort of reagents you're adding into the mix here, can be kind of a leading indicator of your radius of influence that you're seeing. So monitoring those can be really helpful as well. And just making sure that you're seeing the types of changes that you expect from whatever region it is that you're adding. And then lastly here, just a minor point that I just felt like I had to address, though honestly it doesn't come up too often as a concern, is potential unwanted byproducts of these reactions, methane sort of being the predominant one, but usually it's quite transient, and it really honestly doesn't present itself too often. And believe me, I would be getting calls all the time if this was something that was really presenting itself as a concern on site after site. So it's just something to be aware of, particularly if these injections are happening, below a building with a big concrete slab or something, right? Just something to be aware of. And I know, we're speaking all about bioremediation strategies up to this point, but there's a lot of synergies that we can get with combining all of these biodegradation approaches and with other technologies, and particularly sorbent technologies like activated carbon. All of these different technologies that we're all going to be presenting on today have, various strengths and weaknesses. So anytime we can combine things together, we can get a lot of synergy and often maintain a much higher level of efficiency. And, in turn, the overall goal always is to have a more effective remedial strategy that is both cost effective, quick, all of these things to consider. And when we're talking about the combination of sorbents and bioremediation specifically, having something that we can co-apply with whether it's an electron acceptor or an electron donor, that enables you to see a really rapid drop in the dissolved phase concentrations, which is something you see with sorbents like activated carbon, is really advantageous and helps you sort of see an immediate reduction in the overall risk profile. And on top of that, we can actually encourage the biodegradation mechanisms that we're trying to encourage here by helping create this sort of growth matrix. So a little bit about just kind of the basics of how these bacteria operate. And I know the little graphic I showed of sort of plucking off the chlorines from the PCE is sort of completely at odds with what I'm about to say here. But, bacteria do not sort of float around freely like tadpoles or something. They're really more on these biofilms. And they're not like going out and hunting and seeking out food. Things have to come to them for these reactions to all happen, right? So we can end up in situations when we're talking about natural, sort of intrinsic bioremediation, where if the concentrations of the contaminant are too low, or the bacteria, just are not able to then have enough food source to ultimately do these reactions in an effective way, the populations will decline, and ultimately, it's not going to be efficient if we don't have essentially enough of this biofilm growth for the bacteria to thrive here. So what adding in activated carbon can help us achieve, of course, the immediate sorption is a huge benefit, but can also help with this biofilm biomatrix formation. So a little just sort of guide on that. FlumeStop here being REGENESIS colloidal activated carbon product, but in any case, we apply the activated carbon here, contaminants absorb onto it. That's a pretty simple process here. But then also that biofilm starts to grow. So we have that promotion of the biological degradation, and we almost always are going to, again, this is a combined remedy approach in all likelihood, where you're co-applying with some sort of electron donor or electron acceptor, or maybe some sort of abiotic mechanism. But in any case, those sorption sites are regenerated as we ultimately degrade those contaminants into things that are not readily sorbed activated carbon. And then as contaminants continue to either flux in from up gradient or diffuse back out from some of those lower permeability zones, you have the activated carbon that's there and still present and sort of ready to absorb those contaminants, and the cycle can continue on. So I wanted to highlight a case study here that really is a true combined remedy approach. This was a site in Indiana where we had a pretty big plume that was migrating to the river. Not fun, not great. And this TCE plume had, well, basically we were trying to address it pretty aggressively and pretty quickly. And in fact, there was a thermal treatment done sort of at the source area here, as well as treatment with some combined approach with a zero valent iron and an electron donor to encourage that both abiotic and biotic degradation of the TCE. And then sort of along the plume as well, you can see a little bit these dotted black lines here, which were sort of strategically placed in the roadways, so they had access to do the work. This was treated with colloidal activated carbon and a zero valent iron, as well as this EDI plus here. This is adding in the appropriate microbes. So we actually bio-augmented this as well. And over time, we saw a really nice and rapid decline in the concentrations. But just skip ahead here real quick. We were able to see a really nice rapid decline in the concentrations 3 months post-application. We saw like an 80 to 100% reduction in the total CVOCs, depending on exactly where you monitored, and saw a really significant decline in the concentrations with a drastic reduction in the plume length and basically very minimal CVOCs actually impacting the river now with the primary receptor here. Now, I wanted to go back really quick here on the way we were able to optimize this design a little bit, utilizing those fluctuation tools that I mentioned earlier. And again, particularly when we're talking about these barrier configurations, having a really good handle on the contaminant mass flux is huge. And in this scenario here, we were able to implement these tools where you get this nice vertical resolution, and we did it sort of along the length as well. And so with that, we were able to cut the total barrier length and also sort of dial in our dosing into the area that had some of the highest contaminant mass flux and the highest RC velocity. All right, so I wanted to briefly just touch on some other tools and things that can be helpful for site assessment and characterization in general. The image here I've got, this is a biotrap sampler, which can be really helpful if you're trying to sort of test different remedies in the field. It's sort of like a nice combination of a bench test and a pilot test where you're effectively doing a bench test, but under like true field conditions. But on top of that, obviously, there's tons of other molecular biological tools that are in the toolbox now. qPCR analysis, some of these next-gen sequencing, compound-specific isotope analysis, stable isotope probing, all of these can be really helpful for diagnosing and also in sort of demonstrating that biodegradation is really happening. Not on the bio side of things, but just in general, high-resolution site characterization tools are so important and so helpful. Various direct push technology tools, you know, like cone penetrometer testing to really understand you know, the geology we're dealing with, MIPS and hydraulic profiling tools, laser-induced fluorescence, like Paul was showing us earlier. All of this is so helpful and so critical to have a really good understanding of our conceptual site model. And then lastly here, just, you know, there's various software tools as well that can be employed potentially when you do maybe have some of these data gaps to sort of help smooth things out a little bit with some like geospatial rigging and things like that. So just other things that can be employed to help us get a better understanding of the site. And overall, just some recommendations, lesson learned that I wanted to point out here too. Again, really having a good understanding of the geochemistry and Any adjustment that may be necessary is so important to make sure that we're set up for success. This doesn't come up too often, but particularly if you're employing some sort of bioremediation strategy via, an injection well network, some degree of well fouling is expected, and you just have to be sort of prepared to take that on down the line and rehab the wells if need be. I know I said it before, but I'll say it again, having a really well-defined performance monitoring program is key, so that you can make educated decisions on when maybe you're ready to switch over to a true monitored natural attenuation approach, or when you can say definitively, this contaminated site's been addressed and we can close it out. And then just another point that, based on that monitoring, it's entirely possible that in some scenarios a reapplication might be needed. We often are designing these things to be a single application, but sometimes we're not, and it's important to understand that on the front end too. Is this design intended to be one application every 3 years for the next, 10 years or something, or is this really intended to be a single application event? And it's always going to be a matter of sort of striking the right balance. Certainly choosing the right reagent that is going to be reactive with the contaminants of concern, that's sort of like, in my opinion, sort of like step 0, right? If you don't have that, then you have nothing. And that's usually pretty easy to diagnose on the front end, whether you're choosing something that's chemically compatible with the contaminants that you're trying to address. But then, there's some more logistical things, right? Are you able to actually apply it on the site here and able to get that appropriate contact into the subsurface? And then ultimately too, what's the longevity of the reagent that's been selected? Some of that back diffusion is always going to happen, and the longer lived your remedial reagent is, the less you see those effects. Again, every site has heterogeneity to it, even if it seems to be pretty homogeneous. There's always going to be those zones of higher and lower permeability. And over time, you're going to get that back diffusion out of those lower permeable zones. And that's where we see that rebounding happen. But if you have a much longer lived reagent, it can sort of stick around and help take care of that. And that is really one of the primary advantages of adding in something like an activated carbon into these treatment approaches, because while the sorption sites certainly have a capacity to them, the reagent itself is not, getting spent and consumed. And I just wanted to highlight too, this is a really dynamic process in general. We, despite our best efforts of, doing really good data collection, and you're going to hear a lot of us over the rest of the day talk about, higher data resolution and high-res site characterization and all these things that we love to see. But even in the best case scenario, there's still so many unknowns, and it's a dynamic process where we put together a design, but then we often need to calibrate it once we're actually getting out into the field and doing these applications and doing the application itself. We want to make sure that we're actually achieving our desired radius of influence, our desired geochemical changes that we can observe in the field. And again, then sort of recalibrate and change these things if needed, and sort of go through it in kind of a cyclical process if need be, and be flexible. So just to wrap it all up here, bioremediation can be a extremely versatile remediation strategy that is applicable to a super wide range of particularly organic contaminants. But it is, like any in situ approach, really contingent on having really excellent site-specific understanding and a really good conceptual site model. Planning on the front end, what that remedial scope is going to look like, as well as your overall monitoring program is critical. And then also certainly always should be considering what sort of combined remedy approaches can be employed to achieve the overall site goals and maintain as high a level of efficiency as possible. And then sort of lastly here, just making sure we're using all of our tools in our toolbox when it comes to site characterization and other advanced tools, so that we have as good a picture as we possibly can. So with that, I don't know if we still have some time for questions. Okay, great.
Just wondering if your nice little animated thing there, your PCD would be integrated through TCD, the DCD. Within the DCD step, where, at what point, or how is it decided, or what is the process that creates cis versus trans? And if you see trans, is it showing you something about what could be committing full degradation?
Yeah, so much more often we are seeing cis than trans, right? Like it is not a common, it exists, obviously we see trans on lots of sites, but so much more often we're seeing cis, and all of this sort of boils down to which microbes are present. And it is, I believe, a more energetically favorable position for it to be in to go to cis rather than trans, right? So it's not as common. I don't have a good answer for you on what that actually would mean, though.
I saw you had a little micro sampler. I'm assuming where you go to, test what constituents of the microbial community are. How exactly does that function?
So that like biotrap sampler, yeah, I mean, essentially there, what you're doing is, it's sort of like having a little, like a little microcosm that you're putting into an existing well or something, right? So it'll have different reagents in there too. And you're sort of seeing over time, put it into the well, let it sit there for some period of time, then pull it out, send it off to the lab, and they can run all their various fancy microbial analyses on it and sort of see, often you're going to be comparing different reagents with that sort of approach as well and see what's more effective on that specific site.
So specifically when you're doing biofilms, that's sometimes something to get like all the members like mirroring because behind layers, especially when you're trying to have like growing on the surface that may not be the same substrate it's growing on. So do you ever have any issues categorizing the anaerobic constituents of the normally aerobic community? So like on the contaminated carbon, whatever, you'll have pockets of anaerobic. Is it difficult to get characterization of that using that?
I mean, certainly there's always, again, there's so much heterogeneity, right? And any sort of discrete sample is going to be exactly that. It's a discrete sample that's not necessarily representative of everything. So I would say I personally am not doing any work where I'm like taking the activated carbon and actually sampling for various microbial populations. I would say if you're not finding them to be prolific and present abundantly though, then they're not prolific and present abundantly, right? If there are pockets here and there where you're not seeing them be prevalent, then they're likely not prevalent enough in that specific scenario to have these processes happen in a efficient manner.
And then just to follow up, do you have an optimal mass flux for, is it contaminant based or is it like microbial community based? Is there, for instance, ask like is there an optimal mass flux if you're trying to do bioremediation?
Oh, I mean, certainly, and particularly if we're talking about a barrier configuration, right? If we're talking about sort of a wide swath of area where we're trying to treat, it's much less dictated by contaminant mass flux and much more dictated by just contaminant mass. But certainly there, and the mass flux, it's sort of like different levers we're pulling, right? There's the velocity and then the contaminant concentration, right? And for the contaminant concentration piece of that, that's going to get into like, what is the appropriate dose, right? How much of whatever reagent we're applying we need. Then for the velocity piece, that gets into what kind of residence time is most appropriate, right? So if things are moving really, really quickly, perhaps we just need to make a wider reactive zone sort of parallel to groundwater flow direction, right? So, but long story short, yes, there are sort of optimal zones, and Paul will certainly get into this a little bit later, but there are absolutely sort of optimal groundwater velocities where if it's too slow, it's going to take you kind of forever to see performance with that kind of configuration. And if it's too fast, you might just kind of blow through your barrier.
Can you just talk a little bit more specifically about, like, you talked a lot about performance monitoring, an ideal setup for performance monitoring, specifically interested in a petroleum site, if you're doing bioremediation, like, frequency analytes, are you doing field monitoring? Are you doing analytical? Like, just very conceptually, what would be like your ideal performance monitoring?
Yeah, I mean, certainly a combination, right? Of the field parameters are huge, right? And they're so easy to collect that it's like every site should absolutely be as possible, right? Just understanding like, what is our DO, what is our connectivity? All of these things are really helpful and highly recommend that if at all possible. Then on the analytical side of things, I mean, certainly the contaminants of concern are also huge, right? What I see sometimes as being an issue is, and this varies state by state, right, on what is regulated. In a lot of states, though, they're really mostly concerned just with the VOCs and SVOCs and not necessarily like the total petroleum hydrocarbons, even though depending on like how weathered this plume is, that really might be what the predominant mass is of some of these non-specifically analyzed VOCs and things that are just making up the overall demand here. And so sort of getting a really good picture of that can be really helpful too, sort of before and after. Now, with that said, up here, typically those are monitored for, right? So that's not so much a concern for Vermont, New Hampshire so much, but I know like I can do a lot of work in New York where they're not usually measuring for TPH, and it's always so frustrating because you're just like, I know your benzene levels, but that's not really telling you the full picture here, right? I don't know if that fully answered your question, but
Well, I guess frequency too, just.
yeah. I mean, certainly immediately following an application in an ideal world, getting like monthly data would be fantastic, but that's not always possible. So quarterly at the very least, sort of on the front end of things. And then once trends can be interpreted based on that, then certainly a decrease in frequency is absolutely acceptable, right? If we're starting to see a trend emerging, then going to, you know, biannual or annual or something certainly would make a lot of sense.
Talking about combined remedies, is there any consideration for if you're deciding to do a targeted removal in source area or something like that, and where if access, consideration more of a concern when you're in a situation where you do one versus the other?
I mean, absolutely, and there's always like, everything has its pros and cons, right? But generally speaking, if we're talking about shallow contamination that is readily accessible and the disposal costs aren't crazy high, that's almost always going to be the best approach, right? You're kind of guaranteed success if you know I'm digging out all of this mass, then you have all this mass that you inherently removed versus these in situ approaches. You know, we know the chemistry works certainly, right? That's sort of not debatable really. It's really just a matter of, you know, getting the right contact and, you know, all these other geochemical factors and things that may be at play. So we can make a pretty good assessment and feel pretty confident in what we're actually going to do, but an excavation is sort of 100% guaranteed success at excavating out things. What I always love to do, if possible, right, is if you're doing some sort of targeted excavation, but you know there's almost certainly some sort of residual mass there, adding in some sort of amendment while you have an open excavation is always really great, whether that's, you know, a chemical oxidant or some sort of bioremediation agent or activated carbon, whatever the case may be. When you have open and free access to an area that you know is contaminated, that's always a great opportunity to add in one of these reagents. And then you know that the contact at least is there, and you're sort of keeping that variable out of the equation.
If you have petroleum impact to a supply well, typically, but yeah, treatment in, it's such a bacterial breeding ground, you have to put it in feed. Can you, presumably there's some degradation going on in that GAC tank. Can you bio-augment the PRB wall, or would that extend its life? Would it help it capture contaminants longer if the bacteria is degrading it as it's captured? Is
Yeah.
that a thing?
No, I mean, certainly bio-augmenting is almost never a bad idea, right? It's more just whether or not it's needed, right? And for most petroleum hydrocarbons, the bacteria are sort of bountiful and present at pretty high levels, so we don't typically need to bio-augment, we very rarely do. And I think something that, I know this wasn't really your question, but just kind of wanted to point out to you, when we're talking about like above ground systems where we're using GAP or something versus below ground systems, we're talking about such a different residence time, right? If we're thinking about like what would be equivalent like bed contact time be for an in situ PRV versus an ex situ system, it's so different, right? Where we're talking about like hours or days, right? Versus months, years, depending on sort of what your groundwater flow conditions are. So, the sorption kinetics in a lot of ways, it translates sort of perfectly, but the actual contact time is so different. So it's not an apples to apples comparison.
You both talked about the importance of field parameters. Do you find maybe things have changed over the years, but I know REGENESIS is typically going to be hired by consultants who work together to implement the plan, and then the consultant takes over. And but usually for money reasons, they're not going to call REGENESIS every time it's simple. Do you find two things that do consultants even know what to do? I'm sure some do, but are there issues with not knowing what the data means, the field data, and the quality of the data? Is it like operating a YSI is going to be dependent on who's operating the data that come out?
Yeah, I mean, the second piece of that, certainly, data quality, that's always a concern, particularly when we're talking about field data versus, lab validatable data and things like that, which we can hang our hat on a little bit more maybe, right? You do the best you can, right? Hopefully they're calibrating their equipment and doing things to collect the best possible data, but sort of to your point, being able to have either folks in the field or in their office, whoever, that are interpreting the data to, at the very least, say like, does this make any sense? Or was this data that you collected garbage for whatever reason, either equipment error, user error, or whatever the case may be, right? I mean, there's a wide degree of variability of, experience and skill amongst the consultants that I work with. I don't want to like bash anybody, but I'd say most folks are able to sort of interpret that data at least superficially in a way that makes sense to them, and at least be able to say like, okay, the ORP I'm getting here is minus 400, but I added an oxygen releasing compound, so that doesn't make any sense, right? On a really superficial level like that, I think a lot of them can certainly make those interpretations. But I think sort of modeling out the changes over time and sort of making sense of that data is something that as an industry maybe is lacking a little bit. But I think sort of a snapshot in time interpretation of like a binary, does this make sense? Yes or no? I think most of the consultants we work with have a pretty good assessment of that, at least. I don't know, there's some consultants in the rooms.
And I mean, but point out that, I mean, regulators too might get the data and not know what it is.
Oh, for sure. And I mean, I certainly like data just dumped on your lap is not really helpful to anyone, right? Like it needs to be, and again, this sort of goes to having a monitoring plan that you from the front end sort of establish the expectations so that you can then make it relatively easy and quick determinations on whether something is trending in the direction you expect or something has kind of gone haywire, right? Because again, we're collecting all this data to put all the pieces of the puzzle together. And if one of those pieces is sort of misshapen, it sort of tells us like, pause for a second, like what's going on here. I guess with that said, me, and I'm sure all the other presenters here, we would absolutely be happy to like answer a phone call. Somebody's just like, can you help me interpret what the field data I'm looking at means? We would absolutely always be helpful to sort of just help and answer those questions, whether that's diagnostically on the front end or on the back end of the treatment. Always happy to do that.
From what you've seen, how much of bioremediation is trying to make the conditions for the nitrate or bacteria such that they perform well, maybe that gear up to metabolism versus trying to introduce something that's specific to a particular treatment where you're actually trying to see the aquifer, see the source zone with the treatment area with bacteria. What is it? 90% it's already there, or is it kind of variable?
I will say I love when we get microbial data on the front end, but it's not super common that I do get that, right? And I don't get to dictate that happen. I'd say by and large, right, for petroleum sites, I think it's sort of generally agreed amongst the industry that those bacteria are generally present at sufficient enough quantities. You can certainly take samples and assess that. But people typically don't, because those assessments are not cheap, right, to run those microbial analyses. And enough sort of literature suggests like it's probably there, right? Now, when we talk about chlorinated solvents, though, certainly not the case, right? They are definitely around, naturally occurring at lots of different sites, but often not at the high enough levels, and often not to completely dechlorinate, right? Where we might have a lot of bacteria that can reduce our TC to cis and then sort of stall out there. So I'd say more often than not, when employing bioremediation strategies for petroleum hydrocarbons, very rarely bioaugmenting. For chlorinated solvents, more often than not bioaugmenting. Again, because it's in the overall scope, it's kind of a drop in the bucket in terms of the cost. And there's kind of very little downside to adding in some extra bacteria in there. So usually we do it.
Can you talk a little bit about performance monitoring with respect to chlorocarbon? It's obviously injected to create a more preferential substrate in part for the biofilms, but it also adsorbs to the carbon as well. So
right.
When we're seeing the contaminants disappear or reduced, is there some evidence in terms of a biological production product that we can see that demonstrates that it's not just being bound up, but it's also being destroyed?
Absolutely, and really like to look for those actual end products whenever we can, right? Certainly, I'll caveat this with things that are either biotically or abiotically degradable. We can absolutely look for some of those end products, usually like those dissolved gases. So when we're talking about chlorinated solvents, we're looking for the ethene and the ethane and methane and things like that are showing us like, yes, you actually have achieved those end products. It's not just that it's sorbed onto the activated carbon, and we can see those changes over time. So that's sort of like the number one kind of line of evidence there, is just looking for those end products being generated over time. The caveat to that being for, again, things that are not degradable readily. So specifically here, really talking about PFAS, where it is truly just sorbing, right? So there we're using our understanding of the groundwater flow conditions to understand like how long will it stay adsorbed to the activated carbon, versus, for other things that are degradable, we're more often than not, co-applying with things to help that degradation process, so that we, regenerate the sorption sites, et cetera. But yeah, we do encourage folks to monitor for those actual end products so that we can demonstrate really definitively it's not just the sorption that you're seeing the performance from, right? You're also seeing that degradation really occurring.
And so are you doing that through like soil vapor monitoring or through actual
You can
ongoing
do
monitoring
the
of ground?
groundwater sampling. So having a baseline is really important though, right? Like there's always some degree of ethene and ethane and, carbon dioxide and all these things, these dissolved gases that are already there. So having a good baseline is really helpful so that we can see, hopefully that increase relatively shortly after the application. Okay, great. Thank you.